Hi Year 12 Maths General students, welcome to another lesson from Unit 3 of the Queensland Maths General syllabus, and today we're looking at the role of the coefficient of determination or R-squared value when we're performing a statistical analysis of bivariate numerical data. The lesson objectives today are reviewing the role of the coefficient of determination, so how do we use this in statistical analysis? And then we're going to go and look at how to calculate the coefficient of determination and apply it to the context of the data being analysed. The coefficient of determination, or R-squared value, is simply just another analysis tool we can use in our bag of statistical values. It's easily calculated if you have the correlation coefficient because you simply just square it and you end up with the coefficient of determination. Now often we then convert it to a percentage by multiplying that decimal value by 100%, and then that gives us a value that we can use to attribute a percentage variation we see in the response variables that can be explained by the variation in the explanatory variable. So once we've determined our R-squared value, we would write some sort of concluding statement like, if the R-squared value is whatever we've calculated, then the percentage that we've converted it into of the variation in the response variable can be explained by the explanatory variable. And just note that the leftover percentage of the variation might be able to be explained by other direct or indirect factors influencing the changes that we see in the response variable. Also, just note that if we're given the coefficient of determination, we can also work backwards and calculate the correlation coefficient just by simply square rooting our coefficient of determination. Let's practice calculating and using this coefficient of determination. So here's just an example of your typical simple familiar question. I've got a sample of students who were measured to investigate if someone's height was a good predictor of weight. As a result, a correlation coefficient, or R value, of 0.89 was calculated. We have to calculate the coefficient of determination and then interpret the coefficient of determination in the context of the data. So A, easily done. Simply just put in your correlation coefficient and square it. 0.7921. Then if I multiply that by 100%, I have a percentage value of 79.21%. For part B, it's essential that I identify in the scenario which variable is the explanatory and which is the response. So if I read the question carefully, sample of students was measured to investigate if someone's height was a good predictor of weight. So logically to me that means our height is our explanatory variable and our weight is our response variable. So if I'm then interpreting the coefficient of determination in the context of this data, that means that an R-squared value of 0.7921 can be interpreted as 79.21% of the variation I see in the weight can be explained by the height of someone. So writing some sort of statement like I've got there where we're saying 79.21% of the variation in a person's weight can be explained by their height. And always keep in the back of your mind what could be the reasoning for the other 21% of the variation. So in this scenario, we could think of things like gender, age, genetics, lifestyle habits like eating or exercise. As long as we're understanding that this data is showing that taller people are heavier and shorter people are lighter as a logical interpretation of the scenario. Okay, let's look at the second useful component of finding a coefficient of determination. It can also be used to assess the strength of correlation as a measure of reliability of any regression line we fit to the data. So when we put in a line of best fit, the closer that your coefficient of determination value is to 1, the better your linear regression line fits or correlates to your raw data points. So if I had an R-square value of 1, that means 100% of my data points lie on the linear regression line. So this is a great visual that I've found from mathsisfun.com, and it shows what we mean by a perfect positive correlation, and then it works all the way over to when we have perfect negative correlations. So again, another very handy way of analysing the reliability of our regression models we come up with. Okay, let's see some more examples where we're tying together both those uses of the coefficient of determination when we're statistically analysing data. So the questions that I have here are both simple familiar. First one's looking at the relationship of two bivariate variables defined by the coefficient of determination, giving us a value of 0.6231. First thing we need to do is calculate the value of the correlation coefficient, so we're working backwards. And then secondly, comment on the strength of correlation between the points of data and a linear regression line that was fit to the data. As always, write down your facts. So our R squared is 0.6231. And then to find the correlation coefficient, I'm just going to square root that. So if we input that, square root of 0.6231. So we get a correlation coefficient of 0.79, which supports a strong association between your response variable and explanatory variable. For B, comment on the strength of correlation between the points. So thinking about the strength, I would probably associate a 62.31% correlation of points to the regression line as a moderate correlation. So I'd write something like 62.31% correlation between data points to the regression line supports a moderate correlation. In this next example, the question says the correlation coefficient R between exam results and hours studied is positive 0.982. Determine the value of the coefficient of determination and interpret in the context of the data. So when we analyse the information we'll be given, this correlation coefficient is in the form where we've got our response variable first and our explanatory variable next. So I'll just document those facts, and then from there we're after our coefficient of determination, so we're just squaring the 0.982, and we get 0.964. Converting that into a percentage, that means that 96.4% of the variation we see in exam results can be explained by the number of hours studied. So put really simply, if you study more, your exam results will be better, which is a very logical conclusion to come to. And secondly, we can say this then supports a strong correlation, so a 96.4% correlation between the data points and the regression trend line if we were to graph that on a scatter plot. In this next example, we're coming back to a scenario we previously looked at, where we're looking into the possible correlation between the time it takes in minutes for a headache to go away when different doses of pain medication were given to a group of 12 patients. So in a previous lesson, we composed the scatter plot and fit a trend line, and you can see there we've got a coefficient of determination of 0.4752. So here the question wants us to use the coefficient of determination calculated from the graph and interpret it in the context of the data. So firstly, when I'm having a look at the correlation of the points that I put on the scatter plot to the regression trend line,
you can see that they don't fit it very well. So visually I would classify that as probably a moderate correlation. We can then confirm this with the value itself. So if I've got an R-squared of 0.4752, that means that 47.52% of the variation I'm seeing in the time it takes for a headache to go away can be explained by the variation in dose of pain medication that was given. I'd write that first point down as something like that. Secondly, this then supports my assessment of a moderate correlation of 47.52% of the data points fitting the regression trend line. This then supports the moderate correlation I see between the data points and the regression line, with only a 47.52% correlation. You would add that to your conclusion. So in other words, the overall interpretation, the higher the pain medication dose given, the shorter the time it takes for the headache to go away.
In our last example, we're just considering again that investigation where people were sampled on their arm length and height, looking to see if there was a predictable correlation between the arm span and height. Now we calculated by hand a correlation coefficient of 0.956, and we just want to check that the coefficient of determination is the same as that generated by Excel on the graph. So we had an R-squared of 0.9143, and then we have to interpret all of this in the context of the data. Okay, so if we simply check that on our calculators, 0.956 squared gives us 0.9139, which is close enough. If we round it to 0.914. The differences we see there would just be attributed to the rounding during calculations when we manually calculated R using the formula. Alright, so now interpreting the coefficient of determination in the context of the data, well, that means that 91.4% of the variation we see in people's heights can be attributed or explained by their arm span. So there's a pretty strong correlation there between your data points and the trend line, which supports what you're seeing visually. So you'd finish it off by concluding with something like that. Alrighty, so take-home messages here. Coefficient of determination is really useful in helping us come up with a calculated value for ideally the influence of the explanatory variable on the response variable. So we say it has a certain percentage of the variation we see in our response variable can be explained by the variation in the explanatory variable. Secondly, we can use the coefficient of determination to support the strength of the correlation between the data points and the regression trend line we establish for our model. Thanks, Year 12s.